button. Yeah, and I realize we only have 1 hour for the workshop. Last year's test had 31 questions, and the test this year is also similar questions. So I think I would start from the middle of the test, if that's all right with everyone. So the plan I'm thinking is to start from question number 16. I find that usually the later questions are a bit trickier than the earlier ones. So or maybe I can even start from these forces here. No, I'll start from question 15, question 16 with this information. Yeah, because usually the earlier questions are about scientific notation and conversion and graphical motion. Right, and then the later questions, they're sort of sequenced in the way we learn the topics, and usually the later questions are the trickier topics. So I think just to make sure we have enough time to cover the later questions, I'll start with question number 16. And then if we have time, we'll go back to question number 1, or any other question that you want us to focus on, because maybe unit conversions and scientific notations you find to be relatively easier compared to the other topics. So we'll look at the topics that you'd want to see after we look at the trickier questions. Does that sound like a good plan? Yeah, good. Okay, so let's look at the information, the general information here. So it's required for the following 5 questions. The head of a rattlesnake accelerates at a rate of 50 meters per second squared when striking its prey. And if a car could have the same acceleration, we are interested in how much time it would take the car to accelerate to a velocity of 28 meters per second from rest. So it's a kinematic equation question as identified there, right? So the first question related to that is to convert 28 meters per second to kilometers per hour. Right, so yeah. Okay, for conversion questions, you always need a conversion factor. Okay, 1,000 conversion factor, 1,000 meters is equal to 1 kilometer. Okay, and 3,600 seconds is equal to 1 hour. Right, so we want to convert 28 meters per second to kilometers per hour. Yeah, I'll usually we separate the number from the unit, so that's 28 times 1 meter divided by 1 second, so that you know which one you want to convert. So you need a conversion factor of 1 meter is to how many kilometers, and 1 second equals how many hours. Okay, looking at our conversion factor, we have 1,000 meters is to 1 kilometer, but we want 1 meter instead of 1,000 meters. That means we have to divide by 1,000 to get 1 meter on the left side. Which means we also have to divide 1 kilometer by 1,000. Okay, so 1 meter will therefore be 0.001 kilometers. We do the same thing because we want for the seconds, we want 1 second. We don't want 3,600 seconds. So if we divide by 3,600, we have 1 second on the left side. We have to do the same thing on the right side. So that will be 2.778 times 10 to the minus 4 hours is to 1 second. But then we can directly substitute our conversion factors now. 1 meter is 0.001 kilometers. and 1 second is 2.778 times 10 to the minus 4 hours. So that will give you 100.8 kilometers per hour for the conversion of 28 meters per second. Okay, so the conversion is quite long if you do it this way. I'll teach you a trick. So if you're converting kilometers, yeah, all right. Right, so if you're converting kilometers per hour to meters per second, okay, you simply divide kilometers per hour by 3.6. Okay. So that's the shortcut there. So if you're wanting to convert kilometers per hour to meters per second, you divide kilometers per hour by 3.6. And 3.6 comes from the conversion factor. If you can see, 1 second is 3,600. Oh, sorry, 1 hour is 3,600 seconds, and 1 kilometer is 1,000 meters. If you divide those two, 3,600 divided by 1,000 will give you 3.6. So that's where 3.6 came from. So that's the shortcut you can use. Now, if you're converting meters per second to kilometers per hour, you multiply, oh, what happened? Multiply meters per second with 3.6. Okay, so that's the shortcut there. So if you can see 28 meters per second, if you convert that to kilometers per hour, multiply that with 3.6, you should get 100.8. Okay. Right. So the instruction specifically says round your answer to 0 decimal places. So your answer should be 101 kilometers per hour, okay, with 0 decimal places. Okay. Yep. So it's worth taking note of this. So then it will save you time when converting kilometers per hour to meters per second, or meters per second to kilometers per hour. Okay. Right, next, we want to calculate how much time the car takes to accelerate, which 3 kinematic quantities have been provided or are known, and marks will be deducted for incorrect answers. So you need to select whichever, how many quantities have been given or implied in the question. So for any kinematic problem, right, we were always filling out this table of facts that will help us find what, visualize what's given, what's not given, and what we want to find. Okay, going back to the problem, that's why it's useful to have the separate sheet for you to refer to. So we are actually given the initial velocity. It says it starts from rest, so that's VI is 0. And then it says we want to reach a velocity of 28 meters per second, so we're given VF. And it has an acceleration similar to the rattlesnake's head, 50 meters per second squared. Okay, and we want to find how much time. So time is actually what we want to find, and we are not given any information about delta x. Okay, so that means you need to tick off VI, VF, and A. Okay, so those are the things that were given in the problem. Right. And you need to 3 things. If you ticked only 2 things, then you will be deducted half a mark. If you ticked more than the 3 things, you'll also be deducted half a mark for every extra answer. So yeah, you might think it's clever to tick everything off. That's actually not as clever as you think, because marks will be deducted. Okay, and then, right, to calculate how much time, so it's still the same question. Which kinematic quantity do we need to find? I think this is a giveaway question. How much time, that means you need to find for delta t, right? And the table of facts we filled out earlier also says we need to find delta t. Yeah, that should be a giveaway question, I would hope. Yeah, so which single kinematic equation can be used to find how much time it would take for the car to accelerate? So it's still how much time, it's still all related. We were just guiding you through the questions. Okay, if you look at your table of facts, it is delta x that we do not know. Yeah, so delta x, there is no information about delta x. And so any equation that has delta x will be useless for finding delta t. Okay, so you can already eliminate anything that has delta x. There's only one equation that you can use, Vf equals Vi plus A delta t. Right? Okay, so I think, yeah. Right? Okay, so I'm hoping kinematic equation problems would be like giveaway questions. I never know. But yeah, if you work through it systematically, I think it will help you answer such questions. And then after that, you will now calculate the time taken for the car to accelerate a velocity of 28 meters per second from rest. Write your answer to 2 decimal places. So yeah, they're all related. We've already picked out the equation, which is this, Vf equals Vi plus A delta t. Vf is equal to Vi plus A delta t. And we want to isolate delta t. One tip I was giving my students in the previous years is, if you want to practice your rearranging, and if you have time, you can rearrange your kinematic equations to isolate all the variables. So for example, this equation comes up quite often, right? You might have noticed that this equation comes up quite often. So you might want to rearrange ahead of time, isolating delta t, rearrange to isolate A, and rearrange to isolate Vi, so that, when you need any of those equations in the test, you can just look at your formula sheet that is already rearranged, and you don't have to do the rearranging at the time of the test. Yeah, and yeah. And if you do the rearranging, and if you want me to check whether your rearranging is correct, you can take a picture of your rearranging, email it to me, and I can check your rearranging. Yeah, and you can do that before the test, up until just before 7 p.m. I'm happy to check your formula sheets for rearranging, if you're not so confident with your rearranging, for example. Okay, so let's isolate delta t, rearranging this. I'll just rearrange this. I think we've rearranged this many times in the past. One thing you can also do to simplify this equation and simplify rearranging is to note that Vi is equal to 0 because the car started from rest. And if you go back to our table of facts, you can see that Vi is equal to 0. So your equation can simplify to, I'll just remove the 0. A delta t, because VI is equal to 0. The car started from rest. So it's then now simpler to isolate delta t. Okay, if you divide both sides with A, okay, any number divided by itself is equal to 1. So it's equivalent to just canceling A on one side. Then you'll have delta t is equal to VF over divided by A. Okay, VF was given 28 meters per second. That's the velocity you want to reach. And the acceleration was given, that's the acceleration equivalent to the head of a rattlesnake, 50. So delta t will be equal to 0.56 seconds. Write your answer to 2 decimal places. So 0.56, 2 decimal places. Yeah. I think if you don't write with the correct decimal place, I think you'll be deducted half a mark for that. So you'll still get partial marks for that. But yeah, it's a pity if you get a deduction. So yeah, pay attention to the instructions as well. Okay. All right, so as we're going along, and if you have a question, just feel free to type it in the chat box. I'm keeping an eye on the chat box. Otherwise, if I don't see a question, I'll just keep going to the next question to save us some time. All right. Okay, so the next one is a free fall question, which also means that we need to use kinematic equations, but we need to use some of the information, our knowledge, conceptual knowledge about free fall. So a batsman hits a cricket ball straight up. So yeah, you can think of this as a throwing up and throwing a ball up and the ball going down. The ball reaches its highest point at 3.5 seconds later, ignoring air resistance. That's your clue for free fall, although we clearly identified it as a free fall problem anyway. How high, we want to know how high the ball reaches before it returns to the ground, and we've given you G. Right, so again, table of facts whenever you're doing kinematic equation problems, fill out your table of facts. Yeah, how high, we want to know how high the ball reaches, so that means that's delta x is what we want to know. VI, do we know VI? It's not from rest, right? It says the batsman hit the ball. Okay. So that means the ball had an initial velocity because it was hit. It did not fall from rest, or it was not dropped. It was hit by a bat. So it should have an initial velocity, but the problem did not give any initial velocity. So there's no information about initial velocity. Okay, final velocity. Do we know the final velocity? What do you think is the final velocity? Okay. Looking at the problems here, there's no number that I can pick out explicitly for the final velocity. But what's the final velocity for the ball? What value can I put as the final velocity for the ball? 0, right? It says we want to know how high the ball reaches before it returns to the ground. So it's at the maximum height. So remember that at free fall, when you throw a ball upwards, okay, during the upward motion, the ball speed will decrease. It will keep decreasing until it will eventually stop. Okay? When it stops, it's at its peak at the highest height of its motion. And then after it stops momentarily, the ball will start to go back down. So it's always the case that when you throw a ball upwards, or if something goes upwards and comes back down, ignoring air resistance under free fall, okay, at the maximum height, the velocity will be 0. Okay? And you can take that maximum height point as final velocity being 0. That's when the ball stops. Okay. And then the acceleration is the gravitational acceleration, negative 9.8 meters per second squared. Okay, we've given you G is 9.8 meters per second squared. That's the number that we want you to use. But when you put the acceleration is a vector quantity, so you should include the negative sign for your acceleration. It's really important that you put the negative sign, especially when you're doing the calculations. Okay, and then, okay, it reaches the highest point, again, highest point at 3.5 seconds. So your time, so the time will be 3.5 seconds. Okay. So free fall problems are quite tricky because of these facts. For acceleration, you need to put the negative sign, and then that will be G for the number 9.8 meters. So acceleration negative 9.8 meters per second squared. If the ball is being thrown upwards, then take your VF to be 0, and then you're looking at the motion when your ball goes to the maximum height. VF is equal to 0. VI is some initial number, and this is the height, delta X. Okay. That's what we want to know. Okay. So select which one is given or which one is known. So VF, okay, we can, that's implied. We can deduce that from the problem. Acceleration, we can also deduce that from the free fall problem. Delta T is explicitly given. Okay, so these are the 3 things that are known or are given explicitly in the problem. Okay. Right. Which kinematic quantity do you need to find in order to find the maximum height? So maximum height is equivalent to the displacement. So yeah, maximum height is this. Yeah, so maximum height, it's the distance that's traveled by the ball. So that will be delta X. Right, so which kinematic equation, which single kinematic equation can be used to find the maximum height, so delta X. So we're still wanting to find delta X. Okay. And going back to the table of facts earlier, it was VI that we didn't know, right? Okay. Because the problem said the batsman hit the ball and the ball went straight up and then down, but it didn't tell us the initial velocity of the ball after it was hit by the batsman. So any equation that has VI, okay, can be eliminated, and there's only one possible equation that we can use for delta X. Okay. Right, it's a relatively long one. You might probably be expecting already that the next question will ask you to calculate for the maximum height. Okay. So we've chosen the equation delta X is equal to VF delta T minus 1/2 A delta T squared. Okay, you can simplify this equation because if you refer to your table of facts, VF is equal to 0 at maximum height, right? At maximum height, the ball stops momentarily. And so VF times delta T, that's 0. You only have minus 1/2 a delta t squared. Okay, and we actually need, we actually know a, that's negative 9.8. Remember to put your negative sign for your acceleration. And then delta t was given to be 3.5. And then don't forget there's a square. So don't forget to square 3.5 when you're putting that in the calculator. So we actually didn't have to rearrange anything here, which is good, right? And then it says specify your answer in meters to 1 decimal place. So that means we need to include the 0.0 in our answer. All right. Okay. Yeah. How long would it be from when the ball reaches the top to when it returns to its initial height? So the ball, so this is, say, this is the initial height. The ball went up, reached the maximum height, and went down. That's your initial velocity that we don't know. Okay, it took 3.5 seconds according to what's given in the problem. It took the ball 3.5 seconds to reach the top of its flight, the maximum height, this delta x that we solved earlier. Okay, how long do you think will it take the ball to reach this point here? Same height as its original height. Right. So how long does it take for the downward flight here? Okay. Of course, you can solve it using the kinematic equations, right? Because you know VF, you know A, you know delta X, you know the time going up. But in free fall problems, because there is no air resistance, going up and going down is actually symmetrical. Okay, that means that the time it takes to go up should also be the time it takes to go down to the original height. So as long as the ball is at the same height, going up and going down, the time, it's symmetrical. So when the ball is here, the motion of the ball there will be the same as when the ball is here. As long as it's at the same height going up and going down, it's symmetrical. So that means the time it takes to go back down will also be the same time it takes to go back, go up to the maximum height, 3.5 seconds. Okay, right? So knowing that concept hopefully should give you like this 1 mark. It's one of those marks I would consider to be bonus marks, but of course it relies on the conceptual knowledge of free fall. Okay, yeah. All right, good. Okay, we'll now go to force problems and Newton's laws of motion. Okay, here, this is a little bit a tricky question here. A woman is standing on a scale in an elevator as it accelerates upwards, and the elevator stops accelerating, but it continues at a constant speed. So first it accelerates, and then it's at a constant speed. Which of the following statements is true? So if you're looking at the statements, it relates the weight of the woman. It relates the weight of the woman when the elevator is accelerating or when it's at a constant speed. Okay, so that means you have to figure out the weight of the woman in relation to the acceleration of the elevator. Okay, so this is a bit tricky because if you draw your free body diagram, Okay. This is the weight of the woman. The object here is the woman. Apologies, I'm referring to the woman as an object, but yeah, semantically in physics, we refer to everything as objects. So the object here is the woman, because that's what we want to find the weight of. So if we draw the free body diagram of the woman, you have the weight force of the woman, and then the woman is standing on a scale. So the scale is supporting the woman. So you have a normal force that is upwards. Okay, so the tricky thing here is that the number that when you're standing on the scale, the number that you read on the scale is actually the normal force. Okay. So when you say weight of the woman, this woman weigh. So when you say how much the woman weighs. Okay. You are actually looking at the normal force. So the woman's weight is determined by the normal force provided by the scale. Okay. So that's why so when you're just the scale is on the floor on your bathroom and you step on your bathroom scale, you are able to read your weight, because in that case the normal force is equal to your weight force, and your weight is determined by the normal force provided by the scale that is supporting you. Okay, so that's a little bit tricky concept to get your head around with. Your weight is equal to the normal force under zero acceleration when the scale is at rest or moving at constant speeds. So to determine whether the woman weighed more or less, we need to look for the normal force instead of the weight force. So we need to be looking at the normal force instead of the weight force. So the net force will then be equal to the normal force minus the weight force. So we take upwards to be positive and downwards to be negative, right? So your weight force is negative, normal force is positive. So this is the net force. And so let's look at the different situations now, because Newton's second law of motion depends on whether you're accelerating or not. Second law of motion. Net force is equal to mass times acceleration, right? That's the second law of motion. So the net force, that's N minus W. Okay. That's the left-hand side of the equation. Okay, and that's equal to mass times acceleration, the right-hand side. Now let's look at the first scenario. So according to the scale, the woman weighed more when the elevator was accelerating. So as I've said here, to get the weight of the woman, we have to be looking at the normal force. So if we rearrange the equation here, the normal force, we get rid of W, so we plus weight on both sides. So the normal force will be equal to mass times acceleration plus the weight force W. Okay, and the normal force, this one gives the woman's weight. Right? So the normal force gives the woman's weight according to the scale, what the scale reads. So that when acceleration is 0, then the scale gives you the actual weight of the woman, mass times gravitational acceleration for this weight force W. Okay, so when the elevator is accelerating, so the first choice here, when the elevator is accelerating, the woman would weigh more, because then you have mass times acceleration plus weight. So you have this added, okay, this one adds on to the actual weight of the woman. So the first statement is actually correct, because mass times acceleration adds on to the actual weight W of the woman. Okay. Right. So the next choice, according to the scale, the woman's weight did not change throughout the motion. So this will be incorrect now, because we can see from this equation here, that the scale gives you a weight that depends on the acceleration as well as the actual weight of the woman, that depends on her mass. Okay. So the second statement is wrong. The third statement, the woman weighed less when the elevator was accelerating, that will also be wrong, but because as we can see, there is this plus side. So it should be adding on. Mass times acceleration should be adding on to the actual weight that you calculate from mass times gravitational acceleration. Okay. And then the last one, according to the scale, the woman weighed more when the elevator was moving at a constant speed. So constant speed, acceleration is equal to 0. Okay, so when acceleration is equal to 0, then the normal force, that the weight that's given by the scale should be equal to the actual weight of the woman. Okay, and that's why this statement is wrong. And the last statement, we must know the woman's mass to draw any conclusions. Well, we need to know the woman's mass to know the weight force, the actual weight force, but we don't have to know the actual mass to know that the acceleration should add on to the actual mass, actual weight of the object. Okay, and so the first statement is the correct answer in this case. Okay. Okay. So I think this is one of the trickier questions in this test. Okay. All right, I don't see any questions in the chat box, so we'll move on. The recording will be made available on stream, so you can go back and listen to the explanation again if that's still sort of confusing to follow. All right, so next, okay, for the next two questions, a 2,000 kilogram car with a velocity v collides head-on with a 6,000 kilogram truck, so a heavier truck with a velocity of minus v. So the velocity, they're both v, so that means same speed. But you have the negative sign, that means opposite direction. Yeah, so if you can just say that v is equal to 10, so they're both moving at 10 meters per second, but the truck is moving at negative 10 meters per second, so that means they have opposite directions. Okay. Which vehicle experiences the greater force? Yeah, this is a tricky one, because say this is vehicle 1 that's moving here, and you have vehicle 2 that's bigger, weighing more, that's moving to the right. So when they collide, Vehicle 1, so the car exerts a force on the truck. Car exerts force on the truck. Okay, but Newton's third law of motion tells you that the truck also exerts a force on the car. And Newton's third law of motion says that the amount of force is the same, but in opposite directions, regardless of whether one is heavier than the other. Okay, so by virtue of Newton's third law, the force should be equal, even if they have different masses. Okay. Which vehicle experiences the greater acceleration? That's where the influence of the mass comes in. Okay, so Newton's second law of motion, acceleration says net force over the mass. Okay, so that means if you have a small mass, that will give you a big acceleration. A big mass gives you a small acceleration. So in terms of the force in question 27, the mass doesn't influence the force exerted by one object on the other and vice versa because of Newton's third law of motion. But the acceleration will be different according to Newton's second law of motion. So the vehicle that experiences the greater acceleration, so as you can see here, bigger acceleration will be the vehicle with the smaller mass. Right. So the car will give you a greater acceleration because of the inverse relationship given by Newton's second law of motion here. All right. Okay, good. Okay, we have time to discuss this question, which is what I wanted, because this question is usually tricky. An object going down the inclined plane, and usually this question, we've discussed this in the lecture. We're doing this in the practice test, so it is usually a very common question that we ask in the tests. So you have here a block that slides down an inclined plane. The block is 2 kilograms and the slope of the plane is 30 degrees. The acceleration is 2 meters per second squared. And for simplicity, we tell you to use g equals 10 meters per second squared instead of 9.8. Right. First question is free body diagram. Okay. Yeah, we always have the weight force. The weight force is always vertically downwards. Okay. And then you have the support from the slope. Normal force. Normal force should always be perpendicular to the surface, so it should be angled as such. And then those are the two forces. The acceleration is downwards, but we don't need to include that in the free body diagram. The worded introduction doesn't tell you anything about friction, but if you look at the choices here, the choices include friction, right? So then the first one is wrong because weight should be vertically downwards. Okay. The second choice is wrong because normal force, as we've seen, should be perpendicular to the surface. Okay, and so that means the last choice is also wrong because weight should be vertically downwards. Okay, so the only possible choice will be this one. So you have normal and weight force correctly drawn as we've drawn earlier. And then you have this frictional force that's along the slope. So this is your slope. Okay. And your object slides downwards, your frictional force should be opposite the direction of the slide. Okay, so that's the answer. Okay, which of the following correctly indicates the magnitudes of the forces acting up and down the slope? So we want to solve now for the force up and down the slope. So here, the slope, let me draw the slope. That's your object. And this is your slope. Okay, your slope is at an angle of 30 degrees. Yeah, 30 degrees. Your free body diagram is as given. Okay, like we did in the lecture when you're doing slopes, sliding down the slopes, it's useful to put your axes. So your y-axis would be along your normal force. So this will be your y, so that's plus y and that's minus y. And then you put your x-axis along the slope, the motion of the object. So this will be your plus x and that will be your minus x axis. Okay, so that, yeah. So notice again how your weight force makes a 90-degree angle with the base of the slope. And then therefore this angle here, will be 60 degrees. Okay, 60 degrees because that's 180 minus 90 minus 30. Okay, the internal angles of a right angle triangle should add up to 180 degrees. And that's why we do 180 minus the two internal angles that we know. Okay, let me redraw the free body diagram rotating the axes. Okay, so that's, yeah, so I just rotate this axis, so that's minus x. This is plus x, that's plus y and minus y. Okay, your weight force is going this way. Yeah. Yeah, we're just rotating the axis there. And yeah, notice how the weight force is making an angle of 60 degrees with respect to your positive x-axis. So you can just also relocate your positive x-axis here if you want. So that's also plus x, and this is minus x. And notice how the weight force is making this 60-degree angle relative to your positive x-axis. And then you have your normal force that's along the positive y, and then you have your frictional force that is along the negative x. So you have this frictional force along the negative x. So that's your free body diagram in the rotated axis. You have a diagonal vector. You have the diagonal force, the weight force. Every time you have a diagonal force, you have to get the x and y components of that force. So you have the x component of the weight force and you have the y component of the weight force. Okay. Right. So yeah, so the yeah, good question. There's a question there. Y plus x is on the left and the box is moving down the slope. So usually the box is moving down the slopes, your acceleration is going down. We usually, it's easier to put your positive axis in the direction of motion so that your acceleration will be positive, right? So that when you do Newton's second law of motion, force is equal to mass times acceleration. If your axis is in the direction of the acceleration, then you have a positive acceleration. And so it's easier to put positive x in the direction of acceleration. So since your box slides down the slope and the slope was oriented so that it's facing left, then we do our plus x to be on the left side of the axis. Yeah, that's thank you for asking the question, because I think that's an important detail that was missed out here in this discussion. Yeah, that's why plus x is in the, but see, plus x is along the downward, plus x is along the downward slope. So when we rotate the axis, we maintain that the plus x would be on the left, because the slope is sloping downwards on the left, towards the left. Okay, good. All right. So so we have our diagonal weight force. We get the x and y components. Remember that the x and y components always form a 90-degree angle between themselves. So they're always perpendicular. That means that the angle, this angle here between the diagonal weight force and the y component will be 30 degrees. Okay, it's 90 degrees between the x and y components. So if you add everything up, the internal angles, 60 plus 30 plus 90 will give you 180 degrees. Okay, now we can find the x and y components. So x components of the weight force. Okay, here if the angle is measured relative to the x-axis, then the x component is cosine theta. So if theta is measured with respect to x-axis, then wx, I'll write it downwards. Then wx is equal to w cosine theta. Okay, so wx is equal to x component is equal to diagonal vector times cosine theta. Only works if your angle theta is measured with respect to the x-axis. Okay, you can only use cosine theta if your theta is measured with respect to the x-axis. Okay, so in this case, to find wx, that would be w times the cosine of 60 degrees. Okay, it has to be 60 degrees, not 30 degrees, because 60 degrees is what is measured relative to the x-axis. Okay. And I think we can find W because the weight force was given. Yeah. So the mass is given is 2 kilograms and G is 10 meters per second. Okay, so we can solve for the weight force. Weight is equal to mass times gravitational acceleration. That's 2 times 10. So that's 20 newtons, okay, for the weight force. So let me substitute the value of the weight force here. 20 newtons for the weight force. So your x component will be cosine 60 is 0.5 times 20, 10 newtons for your x component. Right. Okay, I wanted to point something out here, and this is the reason why I also took 30 degrees, this angle here between the red arrow diagonal weight and the purple arrow vertical y component of weight. This 30 degrees here, notice that that angle is equal to the angle of the slope. Yeah. So if you look at the drawing of the slope here on the left, okay, the angle of the slope is 30 degrees. Okay. And that 30-degree angle for the slope actually translates to the angle between the diagonal weight force and the vertical y component of the weight force. Right. So if you wanted to use the angle of the slope to find the x component of W, so if theta is measured with respect to the y-axis, okay, right? So the y-axis will give you a theta of 30 degrees, right? So notice how 30 degrees, yeah, I don't have a pointer here, but if you look at the 30-degree angle here in the free body diagram of the rotated axis, the 30-degree angle is measured from the vertical component, WY, so from the vertical or y-axis. So if you wanted to find the x component using the 30-degree angle of the slope, and it's the same angle measured with respect to the y-axis, then you should use sine theta. So if theta is measured with respect to the y-axis, then use sine theta to find the x component. I hope my pen did not decide to find the x component. Right. So let's do that. The x component of W will be Wx will be W sine theta. In that case, W is still 20 newtons. We solved from the mass. It will be sine 30 degrees instead of 60 degrees. And if you do that with your calculator, sine 30 degrees is also 0.5 times 20 will give you 10. So you should still get the same value for the x component. It's just that you use a different angle to calculate for the x component. Okay, so the difference is if the angle is measured relative to the y component, then you use, if the angle is measured with respect to the vertical axis, then you use the sine of that angle. If it's measured relative to the x-axis, then you use the cosine of that angle. Okay, right. Yeah, I discussed this particular solution because in the lecture we used cosine theta, but in the test, when you're given just the angle of the slope, it might be faster to use the sine theta of the slope's angle to find the x component. Yeah, but yeah, it will come up with the same answer as long as you use the correct angle. So there's a question here. Okay, so when finding the weight force, how did we know to use 10 meters per second squared, not the 2 meters per second squared acceleration down the slope? And that's a very good question because it's a little bit confusing. So the acceleration was given to be 2 meters per second squared, and you will know that from the unit. Meters per second squared is the unit for acceleration. But the mass was also given. Given the mass is 2 kilograms. Okay, so they're both 2, right? The acceleration is 2 meters per second squared. The mass is 2 kilograms. And to find the weight, it's the mass that you need. Multiply that with the gravitational acceleration, which we said you use 10 instead of 9.8. for G. So actually the weight is equal to 2 kilograms times 10 meters per second squared. So it's the 2 kilograms that we use to solve for the weight rather than the 2 meters per second squared, which is the acceleration. Yeah, good. Right. Yeah, it's 11. So if there's somewhere you need to go, you're free to go. But for those who want to stay, I can stay for some more time, and maybe we can finish up answering these questions related to the inclined plane. Right. So yeah, so we got the x component for the weight. Question 30, which of the following correctly indicates the magnitudes of the forces acting up and down the slope? So the one acting down the slope, is the x component of the weight force, right? So if you see here, here in the free body diagram, let me see. I'll do opacity here, right? So the acceleration is down the slope. Okay, it's along the positive x-axis. If we look at our free body diagram, that's our positive plus x, that's down the slope. And you can see it's the x component of the weight force that is in the direction of the slope, the downward slope. Okay, so that means the component acting so that means the component acting down the slope is the x component of the weight force, which we solved to be 10 newtons. So down the plane or down the slope is 10 newtons. There's only one choice that has 10 newtons down the slope, so that will be the answer. Yeah, because the weight force acting down the slope is the x component of the weight force. Up the plane, so how do we get this 6 newtons up the plane? We use Newton's second law of motion. So second law, net force is equal to so net force along the x, because that's where your motion is equal to mass times acceleration, right? So along your x-axis, you have two forces, the x component of the weight force and the frictional force. Okay, so the x component of the weight force is along the plus x direction and the frictional force is along the minus x. So you have the x component of the weight force minus the frictional force. That's the left-hand side of Newton's second law of motion. That's equal to the right-hand side of Newton's second law of motion is mass times acceleration. Okay, the mass was given to be 2 kilograms and the acceleration was given to be 2 meters per second squared. So we can actually solve the right-hand side of Newton's second law of motion. That's 2. I'll put the units because they're both 2 to avoid confusion. 2 meters per second squared. Okay. So this whole thing, that is the right-hand side of Newton's second law of motion, and this whole thing is the left-hand side of Newton's second law of motion. Right, so now it's only the frictional force that we don't know, because we actually know the x component. That's 10 newtons minus F is equal to 4 newtons. Newtons is kilograms times meters per second squared. So that comes into kilograms times meters per second squared. That's the same as newtons. Right, so we isolate frictional force here. we'll know frictional force is equal to 6 newtons, because 10 minus 6 should give us 4 newtons. Yeah, so that's how you get 6 newtons for the force going up the plane, which is the frictional force. So notice how up the plane is the negative x, and that's the frictional force that's going up the plane, which is 6 newtons. Okay, right. Yeah, so I think that's the question. And maybe let's just answer question 31 as the last question, right? Which is in relation to torques. Okay, so for this is a torque question. So there's a key. The key has a radius of 1.2 centimeters. So that means this is the key here. It has a radius of 1.2 centimeters. Okay, that's 0.01 meters. Yeah, hopefully you can see the text. It's red. Okay, and it's used to wind up a clock with a force of 20 newtons from your fingers and thumb. So here you have here the finger. The finger here is exerting a force of 20 newtons. So this dot, you can imagine it as an arrow, the arrowhead that's going out of the screen, because your finger is pushing on the key going out of the screen. And your thumb, okay, let's indicate that with the arrow tail. Your thumb is pushing inwards. That's why you're seeing the tail of the arrowhead. Your thumb is pushing inwards with a force of 20 newtons. Okay, right? And the radius of the key is 0.012 meters. 12 meters. Okay, the question is, which are the minimum and maximum magnitudes of torque that you can apply to the key? Okay. So the minimum torque, that will always be 0, because that's when you're not pushing or you're not pulling. You're just holding the key like so. And so, oh, yeah. Or you can also think of the minimum as when you rotate the key and your fingers are parallel to the pivot point here, the axis of rotation of the key. So you'll have a 0 minimum. So there are 2 choices. So minimum torque will be 0. That's when either you're not pushing on the key, or that's when the moment arm is 0. Okay. So there are 2 choices with a minimum of 0. Now for the maximum, we know torque is equal to moment arm times the frictional force. Right. So the moment arm would be the radius of the key, because then the key will rotate about its pivot point, about this pivot point at the middle here. And when your thumb is perpendicular to the radius, then you have the maximum 1.2 centimeters or 0.012 meter moment arm. So the torque for maximum torque for the thumb, for example, will be equal to 0.012 meters for the moment arm times the 20 newtons for the force exerted by your thumb. So that will be 0.24 newtons times meters for the maximum torque provided by the thumb. But your finger is also pushing on the key, so you'll also have a maximum torque for the finger. So that will also be 0.012, the radius of the key, times, yeah, the problem said the finger and the thumb are exerting the same amount of 20 Newton force. So that will still be 0.24 Newton meter for the maximum torque for the finger. So overall maximum torque will be the torque provided by the finger plus the torque provided by the thumb, 0.48 Newton meter. So it would be that last one, 0 for the minimum and 0.48 Newton meter for the maximum. Yes, the minimum torque. So the question is the minimum torque always 0? Yes, the minimum torque is always 0, especially when you're rotating. Because when you're rotating a crank, there will always come a point where the moment arm will be parallel to the force, to the force, the orientation of the force that is rotating the object. So the minimum torque will always be 0, and the maximum torque will always be equal to the maximum moment arm times the force, the maximum force. Okay, is there any question in the test that you want us to go over with to finish off? Because this is the last question in this test. We've pretty much discussed half of the test. So let's see what's in the beginning. Right, so here is writing in scientific notation. So yeah, so let me know if there's a particular question number that you want us to go through. Otherwise, we can wrap up. Yeah. Yeah. Okay, right. There are no, yeah, I don't see extra questions on the chat box, but I will upload the full solution to this worksheet anyway on stream, so you can head over to our Albany folder, class resources folder, and download the solutions from there. Yeah, and good luck with the test this evening. Remember, if you have any questions while you're studying before the test, you can email me anytime. If you encounter issues during the test, email me as well. Yeah. All right. Okay, thanks everyone. I'll see you on Friday, and good luck with the tests.